Hello, everybody. Our next presentation is being brought to you by Mr. Jed Deame, who is the CEO and founder of Nextera Video, and very, very intelligent man talking about NMOS and everything involved with that, as well as many, many other topics. So really looking forward to this presentation on NMOS Evolved Beyond Routing Control. So take it away, Jed.
Okay, thank you very much, Wes. Appreciate you doing the kind introduction. So yes, today we're talking about NMOS. For those of you that don't know us, we're providers of IP core solutions for 2110 and NMOS to help customers add IP capability to their products quickly and easily. So today we're going to walk through a little bit of details on what are the different parts of NMOS, how does it work, explain it to me like I'm a 6-year-old kind of thing. So, we're not going to get too deep into the technology, but feel free to ask any questions that you want. This is more of an introductory to try to give you a working knowledge of what this NMOS stuff is all about. So we'll talk about the required components. There's a bunch of IS numbers and some optional components here, which are BCP, best current practices, and then some of the under development pieces, which are really interesting, taking NMOS in a whole new direction. And we'll see how you can get your hands on it yourself and play with us. Okay, so to begin with, what is NMOS? Well, it stands for Networked Media Open Specification, and it was developed by the AMWA, Advanced Media Workflow Association, and kind of delivered in the format of this open specification to allow vendors to quickly adopt it and implement it in their products. What does it do? Well, it enables control of ST2110 devices, and it enables them to seamlessly interoperate. In the early days of 2110, there was a lot of typing of IP addresses and let's connect to this stream, and it was a lot of manual effort. And customers didn't want that. They want it to be just like an SDI infrastructure. You just push a button on a routing panel, connect A to B, life is good. So that's, in essence, what NMOS at its lowest level does, is lets you go up to your panel and hit destination source take, done, right? But a lot of stuff happens behind the scenes, and you get a lot of other benefits being software-based, the biggest of which is plug and play. So plug and play and push button simplicity. So what do I mean by plug and play? Well, in SDI world, you plug things into a router, and if you do a take, if the signal's not there, you may or may not know it. You might not know what format's coming into the router. You might not know the bandwidth or any of those things. Well, NMOS can handle all that because it's software-based and it's using switch infrastructure. So this diagram kind of walks through how ISO 4 and ISO 5 work. ISO 4 is the registration component. So when you power on all your devices, so you got 3 cameras on the bottom, for instance, 2 cameras and a monitor. As soon as you power those on, they reach out to the registry and they say, hey, I'm here, I'm alive, I'm a camera, I'm capable of 720p and 1080i, or I'm a monitor, I can do 1080p and 4K P30, but I can't do 4K P60, those sorts of things. So the control panel can then just query this registry and see who's out there. And it can even fill in the little button panel and say, I'm a camera with this resolution capability, or I'm a monitor that does this, and make it really easy for the user to be able to select his destination source take. So what happens when somebody does that? Well, somebody says, I'm currently connected camera 1 to the monitor, I want to connect camera 2 to the monitor. How do we do it? Well, we do destination monitor 1, source, camera 2, take. That sends a message to the receiving device, this monitor here, and it says, please, Mr. Switch, Mr. Cloud in the middle here, give me that stream, right? These cameras are all transmitting their streams normally, but the switch stops them. It's not going to send everybody unless you ask for it. So the monitor says, hey, I'm going to do this IGMP join to that stream. And by the way, disconnect me from the other stream. You can do it before or after. There's a few ways to do it. Normally, you disconnect the other stream and you connect to the new stream. So just by the destination sending a request to that switch, he can get those signals. So that's the basics of NMOS. This is how you connect A to B. How is it accessed? It's called an API, an application programming interface, which is fancy words for saying, here's the way to talk to my device. And it's a simple API. It's a web-based API, meaning you could go in with a web browser and you can access most of these things. You can get to them through the http:// whatever the IP address of the NMOS node is, /x-nmos, and then whatever endpoint. There's lots of endpoints, and there's a few examples here. There's this, you can look at the self to get some of the node properties, senders, receivers, maps, security certificates. All these things are readily available through a web browser, through HTTP GETs. You can also do HTTP posts or puts to tell the device what you want. So rather than typing a bunch of things at a command line or writing a bunch of registers, this is a layer that abstracts all the details of your 2110 hardware away and makes it real easy to program, to get to from a user perspective. So this is digging one layer deeper below that. Let's say you're a manufacturer that wants to add 2110 capabilities to your product and NMOS on top of that. How would you do it? Well, this big rack-mounted box kind of shows all the components. You'd have inside the node, you'd have some kind of processor that's running, that's listening to these requests, these NMOS requests on the top left here. And then in the bottom, you've got your hardware that's managing the streams, your 2110 FPGA cores. And he needs parameters, right? His registers need parameters. Well, this software layer on the upper left, NMOS takes this high-level command of switch, subscribe to stream, 1.1, and translates that into the code that the core needs to create it and connect to that stream. It tells the transport, connects to this traffic, and by the way, it all happens under a synchronization to PTP, so we can remain frame locked as we like to be in broadcast. So first, let's look through the required components in a little bit more detail. We talked about 4 and 5 a little bit. We'll also talk about why is it important? Well, EBU has a pretty good document called Tech 3371 that says if I'm going to build an IP facility, what kind of things do I want? It's called minimum requirements to build and manage an IP facility. And you can see it's got NMOS all over it. It says you shall use 04, 05, 07, 08 to guarantee interoperability, make it easier for broadcasters to build facilities and buy equipment that interoperates. Back to ISO 4, again, this is this node API, this thing that will listen to web-based commands. It's also got a registration API that allows these devices, when they wake up, to talk to the registry. And then that same registry has this query API that allows controllers to get to it. So that's really 3 pieces that are specified in this part of the spec. It's pretty basic. And I even gave an example for the query API. Any web browser or any controller can connect to this the IP address /xnmos, yada, 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 and it can see the devices, the senders that are on the network in this case. So that's the discovery. That's the plug and play, how the registry gets to know everything that's on the network. How do I do a switch now, which is usually the first thing you want to do? That's ISO 5. It's called connection management. So it's another API that says, here's how to tell an NMOS device to subscribe to this stream. And that's called an activation in NMOS terms. There's 3 ways you can do an activation. You can do it immediate, relative, or absolute. Examples are like now, which is most common, switch right now, this instant, switch in 5 seconds, or maybe switch at 12 o'clock p.m. if you like. So, okay, so we know how to register devices, we know how to switch, that's the basics. But there's so many more layers that you can build on this. Once you've got an IP connection to every device, you've got a connection to a control system, what else could we do? Well, we could do things like event and tally. So instead of having a separate custom interface, proprietary interface between switchers and cameras, why not use standard NMOS type flavor? And that's what ISO 7 gives you. So ISO 7 is a way, in this case, to do like light up a tally light on a camera. And the switcher, for instance, when you select a source on your program bus, he wants to light the red light on the camera. How do you do it? Well, he sends commands following this block diagram. I won't walk through every step, but you can see you can send either WebSocket or MQTT requests, 2 different types of IP messages. Some work well in big systems, some work better in small systems. Goes to the receiver, and the receiver can then light the light on the camera. So no separate wires need to be run, no separate protocols. It's all just part of NMOS. Next, audio mapping. In SDI, you had the ability to de-embed and shuffle audio and re-embed, but it took extra hardware blades that you had to plug in your router. It was a lot of extra effort. Well, in IP, we don't need to do that because every stream every essence stream is sent independently. So you get a video stream, an audio stream, and an ANC stream. The audio streams can be sent different places. They can be shuffled, and you can do whatever you want with them. So this API is a way of specifying these inputs and outputs in maps. So it's a way a receiver can say, well, I want to listen to channel 3, 4, and 5 from stream 1, but channel 1 and 2 from stream 2, and let's put those together and send them out my SDI output if I'm a gateway, for instance. So this audio shuffling and mapping is now all done virtually without any extra hardware, and there's an NMOS API that specifies what commands to send to do that mapping. More practical example, we actually did a demo right here in this location a couple years ago of this kind of mapping, and this is what an interface would look like if you wanted to map your audio inputs. In this case, there's 2 channels, there's 2 streams, stream 1 with 8 audio channels and stream 2 with 8 audio channels, and we could map those to your 16 channel output that what might be embedded into an SDI stream. So what it looks like is the input, like in this example, the upper left, we had decreasing amplitude from channel 1 through channel 16, and we just did an inversion. So we kind of swapped channel 16 to channel 1. So a very simple audio mapping. So you can see the Nextera gateway output was inverting that audio, that harmonic audio stream. Okay, well, what else can we do in NMOS? Well, one of the things that we found early on was configuration was one of the more challenging parts of the system. Once it's all up and running, it's great. You click a button, you route A to B, easy. Well, how do we optimize the configuration process? How do we make it easy for every device that's plugged in to figure out, well, what's my PTP grand master domain, and what's my announce interval, and what version of NMOS am I running, or am I doing secure and unsecure? So that's what ISO 9 specifies. It's this thing called system resource, which is just a little program that's running on a little PC. It could be a little NUC server. It could be something built into your control system. And it's advertised constantly. It's saying, here I am, I'm your DNS SD server. You know, come talk to me if you're a new 2110 device, and I'll tell you everything you need to know. So you power up, you get all that info, and it can be set automatically. So some human doesn't have to run around 1,000 pieces of equipment and type in all these different pieces of information. It can go extract it automatically. Big time saver. So those are the parts that are called required under the EBU tech recommendation. There are some optional components that we can talk about next, which a lot of facilities have chosen to implement, especially this one, this BCP 00201, which is a grouping. As I mentioned, in 2110, the streams are sent independently. Video, audio, ancillary are 3 different streams. It'd kind of be nice to know that those 3 go together. Those are all from server 1, for instance. So this natural grouping is a way where we can tag these. We can create these tags and say, this video, audio, and ANC go with a particular device. So kind of example here, this thing we're calling playout master. You can name it whatever you like. Playout master happens to have this video, audio 1 and audio 2 group in it. And you can also set roles. So you can say, I got a role of primary, my audio 1 is 2 channel, my audio 2 is a 5.1 channel. A little easier for when the human's looking at the control panel to see what am I actually switching, what am I clicking on here. Works great. One of the things though is it's not really standardized on exactly what to call these, and it's also not, it's still problematic if you've got 100 cameras that are from the same vendor that all show up, or 100 audio boards. So how do we deal with that? Well, this thing is hot off the presses, 00202, called Asset Distinguishing Information. So this is a recommendation that says if you're a provider of ST2110 hardware, please follow this very simple spec that says, I'm going to put my name as a manufacturer, I'm going to put the product name, it's a camera, it's this model, whatever, but I'm also going to put a unique instance identifier. It could be your MAC address, it could be some universal number so that if someone's trying to find box 37 out of 100 in a rack, he can go find it. And he knows which one it is, and he can see where it is on his control panel and his control system. The other thing we added is the ability to put in a function. If you've got a multi-function device, a programmable video processing box that could take on different personalities, then you say, well, I'm currently programmed as a decoder or a format converter or a multiviewer or whatever. That's a function that's advertised. So again, trying to make it easy for the poor guy that's having to put this whole system together, and he's got thousands of devices that are just all look the same. So brand new, hot off the presses, highly recommended for any manufacturer. Next is a relatively recent one, BCP006. This is, how do we do NMOS for compressed video? We've done it for uncompressed, well, but if I'm sending compressed video, I need to know a few more things. I need to know like the bit rate and maybe the profile and the level. So that's what BCP006 does, specifically for JPEG XS, which is becoming more and more popular in this industry. A set of specifications that say, here's how I exactly lay out what my capabilities of my stream are, so I can communicate between the sender and the receiver, and I can use it for my plug and play so that my control system knows, like, oh, this is a JPEG XS transmitter and this is a uncompressed receiver. I'm not going to let you connect those two together. That would be bad. It's not going to work. So it would actually disappear from your routing XY grid. It wouldn't let you do something that's not going to work. Another plug and play smart feature that you get by taking advantage of this. It sees that video-/JXSV field, and it knows it's not the same as uncompressed. Okay, so that's a bunch of little kind of features that make things easier, make things work better. What about security? That's usually the first thing people say, oh, you're telling me to put all my video on IP, you're telling me to do my control on IP. There's hackers out there, you know, inside my facility and outside. How do I keep my content controlled? So big effort, many-year effort that's resulted in some published specs on how to maintain the integrity of your data in your facility, maintaining confidentiality, making sure that you know who you're talking to with identification, making sure that the data hasn't been tampered with, making sure that somebody's actually logged in and authorized to do this thing that you're asking to do. I want to connect A to B. I want to put my cell phone camera on air. Well, no, you're not authorized to do that. I'm sorry. So we'll walk through some of the specs that do that. It's a couple, three BCPs, 003-1, 2, and 3, and then there's an IS as well. The first one is very simple. It says use TLS. What's TLS? That's HTTPS, which pretty much every website now requires you to use. And you get a big warning on Google. It's like, oh, this is insecure if it's not an HTTPS. So first thing, encrypt all the messages, all the NMOS messages that go from the controller to the nodes, encrypt them so somebody can't go in and intercept them. 002 dictates how to do client authorization. So how do I handle things like roles? How do I allocate responsibilities for individuals? And then the last one is certificate management. Anytime you're doing HTTPS, you've got a security certificate, and it's a bit of a pain to manage this manually. So this specifies a method using EST, enrollment over secure transport, to automatically deploy certificates and automate that whole function. And then there's IS-10, which is the authorization component that ties in with those other three standards. It accompanies them and specifies how we're going to use things like web tokens to authorize this. So we'll talk a little bit about how this encryption and decryption works in the next slide. It'll probably make a little bit more sense with a simple example here. So there's a system called PKI, been around a long time, public key infrastructure, that's used for encrypting, decrypting, and authenticating. And it's a combination of public keys and private keys. So in this very simple example, two people want to talk to each other securely. Bob wants to send a message to Alice. So Bob says, give me your public key. So this is a plain text key that she can give to anybody. You can put it in your email signature if you want. Say, if you want to send me a secure message, use this public key. Her private key, she doesn't give to anybody. But if Bob encrypts the message with that public key, then Alice using her own private key, can get the decrypted answer. And that same technology is used in NMOS to send these secure messages. So how exactly does it work in my system? How do I add security? What other components do I need? Well, you know as a minimum, you've got a source and a destination and a controller. That's the starting point. Well, what new pieces do I need if I want to do this securely? Well, I'll need this thing called an authorization server. He's the guy that's going to make sure that I'm legal to do the things that I'm requesting. So the broadcast controller isn't just going to send a command to the hardware directly like it does today. It's going to go to the authorization server first and say, hey, user 123 would like to do this thing. Is that okay? And he'll come back and go, yes, that's fine. He's authorized to do that function. Here's a token, a JWT. And now the broadcast controller will use this token to send the activation to the source. So the source is getting a request and it's getting a token. Well, how do I know that token is good? Well, okay. Well, I'm going to check that with the public key of the authorization server. And then I've got my private key. I can authenticate that and say, yes, that's a valid JWT. I'm going to do the request, which would be like turn on your flow. So now I've turned on my flow, but as we showed in the first diagram, it's going to stop at the switch. It's not going to go anywhere until a receiving device requests to join that stream. So similarly, the controller sends the receiving device the same activation with the JWT. He authenticates it with the public key from the server, and it goes, yep, that's a good request, subscribe to that stream, and then video flows from A to B. So now we have a secure environment, so we don't have to worry about some bad actors getting in and sending video the wrong place, or somebody accidentally doing something that they shouldn't be doing. So there's a lot of technologies that we talked about. This is more just for the slides for people that download these later, but this is a list of the technologies that are used. They're all technologies that have been around for a long time, and definitions of those, so you don't have to look them up. The Cipher suites, again, are listed here. There's different types of, I'm not going to go through this eye chart, but different types of encryption schemes that are possible within NMOS. The elliptical curve Diffie-Hellman ephemeral is one of my favorites, but that's more follow-up activity for the reader to learn more about that if he wants to, or come see me afterwards. Okay, so we talked about some of the basics and some of the add-on features. That's great. We solved the problem of plug-and-play secure control in a network facility. Well, what else can we do with NMOS? Okay, well, let's take a look. Well, as we start looking more and more and evolving 2110 into other markets like Pro AV, there's this IPMX initiative, which you'll hear more about later this week. It's extending into HDMI type realms, Pro AV. So things you might want to know are things that you get on HDMI is this thing called EDID. It says, what are the capabilities of my display? What are the capabilities of my receiver? How can I make sure I'm not sending an incompatible stream between A and B? And this ties back a little bit into what I was talking about with the JPEG XS. It's all more of this plug-and-play information that a node can send to the controller and say, here's what my capabilities are. So in this first example, a sender and a receiver support 4K P60 or 1080p60. They could do either one. So the sender is set to 4K, for instance, and the connection is made. So 4K is being sent from the sender to the receiver. But now a second receiver comes in and goes, well, I want to listen to that same stream, but I can only do 1080p. In a Pro AV world, a broadcast world, this wouldn't come up. But in a Pro AV world, you want that second receiver to get that signal. So you would then tell the sender, okay, you need to handle the least common denominator. You need to back down to 1080p because that's the least resolution, that's the common resolution that both of your receivers can handle. So again, not so much for broadcast, but by presenting this information to the controller, it can make some smart decisions like this or prevent you from doing things that you don't want to do. And this kind of ties in with EDID as well, so that the 2110 devices will be able to query their monitors that they're speaking to over HDMI. You can't do it with SDI, right? But if you're talking to an HDMI display, you can find out what its capabilities are and present those to the controller, so he can prevent you from doing things you don't want to do. The next one, it's like, well, this is operational control. Well, if we can do switching and we can do basic routing from A to B, what about operational control? What about actually configuring these boxes? Because you've allowed me to connect all the devices, but I still have a different API for every piece of equipment in my rack or in my studio. Wouldn't it be nice if there was like one common standard way to do that? Well, yes, it would. And 3 or 4 years of activity have been going on to try to make that happen. So that's what IS-12 is. It's a way to try to create a universal control protocol that's a replacement for all the different varieties of ways it's been done previously. SNMP, OpenConfig, EmberPress, they all have limitations. So lots of information you can read up on this following the slides. Media node configuration, another way, like how can I grab the information from my current configuration? How can I make sure that I've captured the configuration of everything in my system? I'm about out of time, so I'm going to just blast through the last couple of these. There's a testing program out. If you want to be able to test devices or test devices you purchased or you manufacture, you can download this NMOS testing program that they use in the JT&M test. You can test all your own devices. You can download a Docker container with the registry in it. You can download this program called Readle NMOS Explorer, and you can run it on your PC and connect to all your NMOS devices and drag and drop stuff. You can buy a nice little program from Matrox called Conduct IP, which allows you to drag in devices and switch them in an XY matrix, much like you're used to. And finally, in summary, NMOS 04 and 5 have been around for a few years now. They're solid, they're stable, they're used in many facilities. They've been through a lot of interop testing. We've solved a lot of the early issues. We're now testing controllers, so most of the interop problems have gone away because controllers are now being tested as well as the nodes. We've just added security, which is sorely needed addition, and we're now extending far beyond that with things like the ability to control. So I think I'm a little over time, but I'll stop there and take any questions if anybody has any. And if not, if you want to meet me on the other side, we'll be doing a little follow-on chat as well. Okay, thank you very much.